Hello, Mr. Claudia here, and today we are going to be studying our new chapter, which is all about the applications of calculus. So we've got a few different kind of concepts we're going to be working through, but we're going to start with an easy one, which is kind of a review, or at least a wrapping up of what we did in our last course with calculus. It's looking at rates of change. And we've always talked about slope and therefore the derivative as a rate of change. So now we're just going to look at it from the context of some word problems. So as a little bit of a refresher, think of the derivative as an indication of the rate at which something is happening. Remember, the derivative is a slope. Now we learned in our last course, the average rate of change is something you would have found before calculus. This would have been the secant line slope. This is where you have 2 points and you use the slope formula. So you have change in y, or y2 minus y1 over change in x, x2 minus x1. The average rate of change is not great, but it's the best we could do before calculus. Now, when we learned calculus, it allowed us to find the instantaneous rate of change. That is, if you recall back to that critical lesson, the tangent line slope. And to find this, we needed the derivative, dy dx. So these two ideas, these two rates of change, one with calculus, one without calculus. And the key words here are average and instantaneous. So for example, consider the following function for height. So I have the height of an object as a function of time. So I could, plot this, or I can imagine this as some sort of quadratic. If I were to look at the secant line, or the average rate of change, I would take the change in y, so that is delta h, over the change in x, or delta t in this case. So I'd have the change in height over change in, with respect to time. Change in height, that is meters, with respect to time. Similarly, if I was looking at this function and I wanted to look at the instantaneous rate of change, or the tangent line, I would look at dh dt. So pretty much the same idea, the change in h over the change in time, and that's the tangent line. So I just illustrate there to kind of show the link between these two. The derivative, dy dx, is really analogous to the delta y over delta x. Rates of change, either of these types, come up, or that is the derivative or the slope, come up everywhere. In the word problems we're going to see, we'll look at some related to physics. If you've studied motion, and we will be later in this chapter, we'll be looking at how we can use derivatives to help us analyze motion. Biology, rate of change of bacteria growth. Chemistry, how fast is the chemical reaction progressing? What's the rate of change of the concentration? Finances, what's the rate of change of profit, or the rate of change of growth of the company? So with that in mind, let's do a few problems here. And we'll start actually with a business problem. So here we have Samsung determines that the cost of producing X dishwashers in their factory each day is given by this function here. See, so that's the cost. And Samsung probably knows what some of these numbers mean. Like this 500, that's probably like a fixed cost, right? It doesn't change no matter how many dishwashers you make. So that's just probably the cost of like turning on the factory, the lights to the factory, and kind of keeping the factory heated. And then you have plus 350x. X is the number of dishwashers you make. So this is probably something to do with, I don't know, the raw materials. Okay, we need sheet metal to make and plastic to make a dishwasher, so we need 350 whatever times the number of dishwashers. And finally, you have a third term here, and this could be labor, the cost of that you have to pay people. And so you get, depends. The more people you have, it gets expensive, but they can do more work. Whatever the way they determined it, we have a cost function. And so if I sub in X, I can find the, if I sub in 50, I can find the cost of making 50 dishwashers. Now, let's find the instantaneous rate of change of C with respect to X. So with respect to X means that X is on the bottom, right? According to what we did here. So we're going to find the instantaneous rate of change. That is a nice way of saying find the derivative. So C prime at X is 500. Derivative of 500 is 0. Derivative of 350x is 350. And this is minus 0.09 times 2 minus 0.18 times x. And what would the units be for that? Well, it would be the y units over the x units. So this would be cost, which is dollars, and x is the number of dishwashers. So this is dollars per dishwasher. Remember, if I just sub in x equals whatever, that tells me the cost of making all those dishwashers. This is the cost per dishwasher, the rate of change of cost. In business, we call this the marginal cost function. Marginal cost function. And it would be the rate of change of cost. Now, the reason I do this this example is we have to get to know this word marginal. Marginal is a thing in business that means take the derivative. Marginal cost function is the rate of change of cost, or the derivative of cost. You could also, as I say in this TOK here, you could also do the marginal revenue function, marginal profit function. Anytime you see marginal, it means that you're going to find a derivative. And consider what the marginal cost function is. Like, this is actually, it's late in the day. The owner of the factory calls down to the manager and says, "Hey, we need like one more dishwasher. Like, what's it going to cost?" And the manager's like, "Oh, God, I want one more. It's so late." And they're like, "Yeah, we can do it, but it's going to be extra. We're going to have to pay some overtime." And so the owner is like, "Okay, well, we need this last one. I need to make the sale." So they do it, but there's an extra cost associated with it. You guys probably actually, this idea of operating in margins isn't just in economics. Consider when you study for your next math test. You might study 8 hours, and that's going to get you, caught up on a lot of material, and then you probably know it very well. But is it enough to get perfect? Maybe not. So let's say you would have gotten a 50%, but doing that extra 8 hours, you're probably going to get 75%. Study for another 2 hours, you might go up to a 77. Then you might be like 2 a.m. and you're like, is it worth it to study another hour? If I study another hour at this point, I might go from a 77 to a 78? So the marginal cost, I've kind of reached my limit. Like, the marginal cost here is not worth it. That extra hour of studying is not worth it for maybe 1 extra % on my test. So we make a decision to shut the book and go to sleep. Anyways, that's an idea of what marginal is. For our intents and purposes, anytime you see marginal something, it means take the derivative. Whew, okay, let's keep going. After that long story, find the marginal cost when 300 dishwashers are produced. Interpret this result. Okay, so the marginal cost, so that's my marginal cost. So that means I'm just going to sub in 300. So I get 350 minus 0.18 times 300. Goes without saying, you're going to have to do this using a calculator. I like to use my regular calculator here just because it's simple calculations and I'm more comfortable and more quick with it. So that gives me $296. So that is the cost per dishwasher when you're making 300 dishwashers. So we have, just to interpret it, the rate at which costs are increasing when 300 dishwashers are made. Let's say per day. The cost of the first dishwasher is probably a lot. You have to get the factory fired up and all the workers in. But then the cost of the 300th dishwasher is probably a small increase. Find the cost of making the 301st dishwasher. Okay, so we're talking about dishwashers here. The cost of making it, not the rate of change here, but the actual cost. So that means I'm going to go back to this function. I want to find the cost of the 301st dishwasher. So that would be the cost of making 301 dishwashers minus the cost of making 300 dishwashers. So I need to find what is C at 301. Well, I'm going to sub that into my equation. So I have 500 plus 350 times 301 minus 0.09 301 squared. So if 500 plus 350 times 301 minus 0.09 times 301 squared. And that gives me 97,695.91. So, and I also need the cost of making 300 dishwashers. So that's going to be 500 plus, oh, we can't see this now, getting carried away here. 350 times 300 minus 0.09, 300 squared. So I get 500 plus 350 times 300 minus 0.09 times 300 squared. And that gives me 97,400. And so we have 97,695.91 minus 97,040, or 400, minus 97,695. So I end up with 295. So that's how much that 301st dishwasher costs, which is pretty good. You can imagine, you know, how much you sell that dishwasher for. Like $500. Oh, you're doing a pretty good profit, Samsung. We know they are. Anyways, that's a business application. Basically about the marginal. Anytime you see the word marginal. Let's turn la page and look at another question. This one ripped from the headlines of a pharmacist. The concentration of a drug in milligrams per milliliter in a patient's bloodstream T hours after injection is modeled by this function. Find the average rate of change between T2 and T4. So we have asking for the average rate of change. So that's kind of our indication, hey, you don't need calculus here. You're just going to use the secant line or the slope formula. So the average rate of change is equal to, okay, the change in y, in this case c, divided by the change in t. So I'm going to take, okay, between 2 and 4. So c at 4 minus c at 2 over 4 minus 2. I guess what I should do now is calculate what c at 4 is, which is 2 times 4, 8 plus 4 to the power of 3. Can I do this one in my head? Why not? Why bother? 2 times 4 divided by 8 plus 4 to the power of 3. Yeah, glad I didn't do it in my head. Whatever. Anyways, and then c at 2 is 2 times 2, 8 plus 2 cubed. So I have 4 divided by 16, which gives me 0.25. Oh, I guess I could have done that one. Okay, so now I'm going to sub those into my slope formula here. So I have 0.111 minus 0.25 divided by 2. And that's going to give me negative 0.0695. And that is in, okay, so the concentration was milligrams per milliliter. And then I'm going to have divided by time, so, and the time was hours. So we see that the average rate of change for this concentration of blood, it's going down at a rate of negative 0.0695 milligrams per milliliter every hour. And that's what we would expect. The amount of, if you take an Advil, the concentration of the Advil in your blood will go down over time, and then when it reaches a certain level, you can have another Advil. So this is sort of the solution, the average solution, the secant line solution. This is the non-calculus solution. I mean, we could have done this in grade 10. Now what if I asked you what's the instantaneous rate of change at t equals 2? Well, to do this, as soon as I see instantaneous rate of change, that is the derivative. Right? So I'm just going to write it up here. I'm going to cram it a little bit because I have a bad feeling about this derivative. So the derivative of this concentration, unfortunately, is going to require the use of quotient rule. I've been doing so many quotient rule questions lately. Derivative of the top is 2 times the bottom, 8 plus t cubed, minus 2t times the derivative of the bottom, which is 3t squared, all over the derivative of, or sorry, all over the denominator squared, which is 8 plus t cubed all squared. Okay, now what are we doing again? I am trying to find the instantaneous rate of change when t equals 2. So, I mean, what I could do is just sub in 2 now. There's probably a marginal call here to make because subbing in 2 now, it's very messy. So I'm going to do a little bit of cleanup, but I'm not going to overdo it because I'm eventually going to have to go to the calculator. So I have 16 plus 2t cubed minus 6t cubed, 8 plus t cubed all squared. And this is easy to simplify even some more. 16 minus 4t cubed over 8 plus t cubed all squared. So I'm just going to go up here. So the derivative, or the instantaneous rate of change at 2, is equal to 16 minus 4 times 2 cubed over 8 plus 2 cubed over, or squared. So I have 16 minus 4 times 2 to the power of 3 divided by 8 plus 2 to the power of 3 all squared. And I get negative 0.0625 milligrams per milliliter per hour. Very similar answer, but not the same. And this goes back to the whole kind of big setup of calculus, tangent line, secant line. The tangent line is very accurate. This is the exact rate of change at t equals 2. The average rate of change is it's an average, so it's only as good as the 2 points you took. So they're not going to be the same number. But they both give you an idea, in this case, of what the drug is doing in the person's body. So that is a kind of classic example of how we find instantaneous and average rates of change. Okay, but we're not done, because we can also talk about rates of change and integration. Now, oh my God, integration we have not done in a very, very long time. We didn't touch it at all in our last chapter, which is on curve sketching. But remember, and hopefully this will be a little bit of a review for us, we think of integration as the inverse of differentiation. In other words, it undoes the derivative. So if I have some quantity and I take the derivative of that quantity, that gives you the rate of change of the quantity. And that's what we've been talking about in this lesson. Again, it's not a terrible lesson. It's just basically a review of the concept. Well, if you have a rate of change, you can actually go back to the original quantity by finding the integral. So that hopefully is a useful illustration. Hopefully helps you remember this. Now, in these types of questions, you're going to find that it's very useful to use the fundamental theorem of calculus. I know for something that has such a nice title, you probably don't remember what it is. But the fundamental theorem of calculus states that the integral from x1 to x2 of some function is equal to the antiderivative at x2 minus the antiderivative at x1. That is where f at x is the function, and f at x is the antiderivative. I know you're thinking, what is this gibberish? What is this? I'm just going to put a little note here. I find this is a little confusing. I would remember this as the way we learned to solve definite integrals. Now, again, it's been a long time since we've done integration, and this is going to be a hurtful wake up, but it's a good way for us to do a little bit of review now. If you remember, an indefinite integral is where you need to find an integral where there are no bounds. And in the context of a word problem, we don't get that. It doesn't really have a context for word problem. But in a word problem, you'll often have a lower bound and upper bound, or lower limit, upper limit. And this is called a definite integral. And if you remember, the way we solve this is we find the antiderivative, and then we sub in the upper value, and we take away the antiderivative with the lower value subbed in. And so that's the fundamental theorem of calculus. You can go back to the lesson. You'll find that the questions you'll remember them when you see them. So when we talk about rates of change, not only can we have derivative rates of change questions, but we can also have integration rates of change questions. For example, the rate of new subscribers or cable TV subscribers in a city T years from 1995 has been modeled by this equation. So when we talk about the new subscribers, so we're not talking about the number of new subscribers, we're talking about the rate of new subscribers. So let's write that, rate of new subscribers. That is R at T. What we want to know is how many new subscribers were there between 1998 and 2002. And so that is we don't want to know the rate, we want to know the number of new subscribers. Well, if you had a question like this on your IB math exam, hopefully your, I'm going to call it our big R at T because it's the antiderivative. Hopefully your spider sense is going off. Oh my God, they gave me a rate, right? And I want to go back to the original quantity. So I'm going to have to integrate. So I'm going to take this rate, integrate it to get the big R, or the antiderivative. And the way I do this is, the integral of R at T dt. So again, we're trying to teach you kind of those key words to be looking for, but the rate is really the giveaway in this question. Okay, so in this question, it's asking how many new subscribers were there between 1998 and 2002. Okay, so this is T equals 3. And 2002, that would be T is equal to 7. So how many new subscribers are there between time 3 and time 7? So new subscribers, okay, well at 2002 there would be, you can think of this at, so this is, the new subscribers here would be R at 7 and this would be R at 3. So I really am asking what's R at 7 minus R at 3? Just can put a little note here, number at of new subscribers in 1998 minus the number in what was this? Oh, this is 2002, and this is subtract the number in 1998. That's what the question is really asking. Oh my God, we can't see anything. The number of new subscribers in 2002 minus the number of new subscribers in 1998. Now, if I have a situation like this, remember big R was the integral. Well, I'm going to lean on the fundamental theorem, right? Because this, I can almost go backwards to the fundamental theorem here. So this is going to be integral of R t dt from 3 to 7. And I'm going to replace this now with the function R, which was given to me, which is 2000 over square root of 1 plus 0.4t to the power of 3. Now I need to find the integral here. Oh my god, I don't remember how to find integrals. Well, that's okay actually. We're not going to go back into finding the integrals. We're going to hopefully, and you'll remember this hopefully, you can actually just type this into your calculator. Just as you're able to find integrals, you can find integrals by hand, but when you're looking for something that's going to be a number in the end, your calculator can do that. So your calculator can't find an expression, but it can find a number. So I'm going to go turn to my calculator. Hopefully remember how to do this. I mean, every function is hidden under the button menu. So I'm going to press menu, go to calculus, go to numerical integral, and I can enter all this. 3 to 7. What do I press here? Control divide just to get a fraction. 2,000 square root, which is right under the x squared. You can't see it, so I'm going to press that. And I get 1 plus 0.4 times, and I always use x's. I made a mistake here. 1 plus 0.4 x, close bracket, to the power of 3. And then this is dx. Okay, and now I press enter, and oh, it spits out an answer. So that gives me an answer 1612.11. Therefore, there are about 1610 new subscribers. You don't see a question with that kind of final answer often in IB, but I am rounding, so I have 3 significant figures. So I can only have 1, 2, 3 significant figures. The last one has to be a 0, so I have to round to 1610. Often you don't see questions where you have to round like that. So I could have done this integration by hand. I just didn't have space, and I didn't really want to burden this lesson with it. If you want to see me solve this question, ask me and I'll solve it for you. But in general, you can really leverage the power of the calculator by using the GDC's numerical integral function. I mean, technically you could have done the same thing up here. We can find not the expression of a derivative, but we can find a numerical derivative using the calculator the same way. I believe we can do it. So menu, calculus, numerical derivative at a point. Again, it can't be the derivative, but a derivative at a point. So let's call the variable x. Let's call the value, it was x equals 2, and it's the first derivative. So the derivative of what? Well, this is the function here. So it was 2x divided by 8 plus x to the power of 3. Okay, and it's going to solve that for me, and it gets negative 1 over 16. If I press Control equals, it'll change it into a decimal for me. So in much the same way, instead of doing the work by hand, I could have just used my calculator. Okay, let's just do this last example then. If there are initially 40,000 subscribers, find the number of subscribers by 2010. So this 2010 is t is equal to 15. What's this? Initially 40,000 subscribers. Again, we have to decode this a little bit. This is an initial condition, or you might even call it a boundary condition. This is not the rate of change, the number of subscribers. So this is initially, so R at 0, big R at 0 is 40,000. Now, once again, I can do this a few different ways, but it's a really quick and easy way to lean on the fundamental theorem of calculus. So I have R at 15, which is what I want to know, minus R at 0 is the integral from 0 to 15 of RT dt. If I sub in some of the things I know here, I get R at 15, which is what I'm trying to find, minus, okay, R at 0 is 40,000, and that's the integral from 0 to 15 of this horrible function, which is 2,000 over the square root of 1 plus 0.4t all cubed dt. Now, if you really wanted to, you could find this derivative yourself, or this integral yourself. I'm going to guess you're not going to want to, so I'm going to take out my GDC. Sorry, I'm just going to rewrite this. R at 15 is equal to 40,000 plus 0 to 15, 2,000 over square root of 1 plus 0.4 t cubed dt. Okay, now I'm just going to use my calculator to do this. So again, the way I do enter a function like this, I press, well, here's a neat thing. Actually, I don't know if you remember this either. I can scroll up and select a previous line I entered. Press enter. Now I can change. I've made a new, a new line, and I can change these values. I can't change the past, but I can change the future. So I'm going to go up here and change this from 0 to 15. And I have all of the rest looks correct. So now I have 6220 plus 40,000. And that gives me 46,220.4. Therefore, there are about 46,200 subscribers. Oops. Oh, you get it. Subscribers. Okay, so that's that. So we've looked at rate of change. An easy enough concept. We just have to be comfortable with some of the language, and of course we have to be comfortable with integrals, which we may have forgotten over this long period of time. Your homework for tonight, you could do the problems in your book. There are a few, but I don't think there's enough. I don't find it's enough practice. So I've given you 6 and 5, so 11 problems in total to work toward. Use your calculator, right? This is testing a concept, not necessarily the your technique, and your answers are there if you want to check them. Good luck with that, and I will see you next time.